Welcome to AI Paper Slop, the YouTube series where we rip apart the latest AI research. Today, we are looking at a paper from researchers at HKUST titled Towards Mechanistically Understanding Why Memorized Knowledge Fails to Generalize in Large Language Model Fine-Tuning.
If you are an ML engineer tasked with fine-tuning models, this explains the exact phenomena you've been banging your head against.
Yeah, the classic issue where your model perfectly recites a new fact, but totally blanks when you ask it to actually use that fact to solve a multi-hop reasoning problem.
Exactly. The authors formalized this failure as the knowing-using gap. And the 30-second core takeaway here is that when a model memorizes a fact but fails to reason with it, it is not a capacity problem. It's purely a routing problem.
A routing problem.
Right. Using a causal intervention technique called cell patching, they proved that injected knowledge gets stored in the early layers, or sometimes the very late layers of the network. But the reasoning circuits that actually process multi-hop logic, they operate strictly in the middle layers.
Which means the knowledge is just sitting there, inaccessible.
Yeah, it's stranded. And the fix they propose is wild. By manually relocating these hidden states, like literally lifting the memorized representations and dropping them into the computation-effective mid-layers during inference, they can instantly recover up to 75% of this generalization failure.
That is, wow. Okay, let's unpack this because I want to break down exactly how they measured this knowing-using gap. They actually split it into two very distinct dimensions, right?
They do, yeah. You have the accuracy gap and the temporal lag.
Right. So the accuracy gap is just the raw difference between a model's ability to recite a memorized fact and its ability to use it downstream.
Exactly.
But the more insidious one is that temporal lag, which is, the delay measured in training epochs between the exact moment the cross-entropy loss drops and a fact is memorized and the moment it finally becomes usable in a reasoning task, if it ever does.
Right. And to map that lag, they didn't just use, toy data sets. They went straight to real-world knowledge graphs. Stark Prime for highly complex biomedical data and Stark Mag for academic data.
So real messy data.
Very messy. And they tested two specific downstream tasks to evaluate the reasoning circuits. The first is chaining, which tests sequential logic.
Like an A to B to C kind of thing.
Exactly. Say the model memorizes that the protein IGFBP3 is expressed in embryos, right? And it separately memorizes that the drug Mechanistically targets IGFBP3.
Okay.
The chaining task asks which drug targets the protein expressed in the embryo. It forces the model to synthesize those distinct facts.
Right. It has to traverse the knowledge graph. And then the second task is intersection, which is basically retrieving attributes for two different entities and filtering them by a specific relation, usually with a ton of distracting noise in the prompt context.
Yeah, so if your fine-tuning data says trifluoralin is linked to glioma and also linked to hypothyroidism, the intersection query is what exposure is linked to both glioma and hypothyroidism.
Got it. And the training dynamics between those two tasks reveals some super counterintuitive behavior, especially when comparing full fine-tuning, or FFT, against parameter-efficient methods like LoRA.
Oh, absolutely. Because the natural assumption for most engineers is that
FFT should just crush it. Right. Because you're updating the entire weight matrix. Every single attention head, every MLP. It should bypass this gap entirely because it has access to all the routing parameters.
You think so? And FFT definitely achieves raw memorization much faster than LoRA.
Right.
But that early memorization, it does not translate to usable downstream reasoning. For the chaining task, FFT hits peak memorization incredibly early, yet it suffers a temporal lag magnitude nearly identical to LoRA.
Wait, really?
Yeah, and they both converge at the same abysmal downstream accuracy. But it gets even worse on the intersection task. FFT actually exhibits a significantly larger temporal lag than LoRA.
Wow.
The model's ability to parrot the fact shoots up almost immediately, but the generalized reasoning takes dramatically longer to emerge compared to just doing a low-rank adaptation.
So if I'm an engineer looking at those training curves, my first instinct is just brute force. Like, we live in the era of scaling laws.
Yeah.
If I take the parameter count from a 1 billion to an 8 billion parameter Lamé model, or if I just aggressively scale up the sheer volume of facts in the fine-tuning data set, shouldn't this routing bottleneck naturally resolve itself?
I mean, more parameters inherently mean more routing capacity, right?
Yeah.
But the paper explicitly shuts that intuition down. If you look at Figure 2, it shows their scaling analysis, and increasing the model size does absolutely nothing to eliminate the temporal lag.
Nothing at all.
Nothing. And furthermore, when they scaled up the number of injected facts, the accuracy gap actually widened.
Oh, man. So it gets worse.
It gets worse. The network becomes hyper-efficient at localized storage and direct recall, but the cross-layer reasoning circuits simply do not scale proportionally. Pushing more data or more parameters at the problem doesn't fix the underlying architectural failure.
Which means we can't just stare at loss curves and validation benchmarks anymore. We really have to crack open the black box and mathematically trace the knowledge through the residual stream.
Exactly. Which brings us to the mechanistic interpretability tool they used, called self-patching.
Right, self-patching. But wait, are we injecting new information during this patch or just moving around what's already there? Because if we just inject external correct answers into the target layer, obviously the downstream probability will spike.
What's fascinating here is that self-patching strictly relocates existing representations from within the model's own residual stream. No new information is injected.
Okay, so how does the actual mechanic work?
You take a source prompt, the simple memorization query, and run a forward pass. You capture the hidden state at a specific anchor position. In this study, they use the head entity token.
Okay.
Then you run the target prompt, which is the complex multi-hop query. At a specific target layer, you override the target's hidden state with the hidden state you just captured from the source run.
So you're literally just taking a representation the model already generated and manually moving it from layer X to layer Y.
Exactly. And then you measure if the probability of the correct token increases at the final unembedding layer.
Okay, let's unpack this. Because the methodology here is a massive upgrade over standard interpretability tools. I mean, if we look at something like causal tracing from the Rome paper, that requires a clean trajectory, right?
Right. You need a baseline run where the model actually gets the answer right, so you can trace which states were causally responsible.
But here, we're studying failed generalization. The model gets it wrong, so there is no clean trajectory to trace. Self-patching lets us study the stranded knowledge directly.
It does. And it also goes a step further than patch scope. Patch scope is great for decoding hidden states into human-readable text to see if the model, quote-unquote, knows a fact at a certain layer.
Yeah, but just because a fact is decodable doesn't mean it's causally active in a reasoning circuit.
Precisely. Self-patching is an end-to-end measurement. It proves whether a representation, when placed in a specific layer, can actually drive the downstream multi-hop logic to the correct conclusion.
Here's where it gets really interesting for me. I like to visualize the LLM's residual stream as this massive manufacturing pipeline, a factory.
Like that analogy.
During fine-tuning, the new facts you inject are successfully delivered to the loading dock. Those are the early layers of the model. And sometimes they get dropped off at the shipping bay, the very late layers.
Right.
But the actual assembly line, the dense attention heads and MLPs that need to combine that raw material with other facts to build an answer, they're sitting in the middle of the factory.
Yeah.
So the raw materials are physically in the building. But the internal logistics network completely failed to route them to the middle layers where the computation happens.
And the trading dynamics we discussed earlier explain exactly why that logistics network fails. Think about the backpropagation math for a second.
Okay.
When you fine-tune a model to memorize a single hop fact, the network quickly finds a local minimum. It stores the fact in an early layer. The cross-entropy loss drops drastically.
Oh, because the loss is suddenly so low, the natural gradient vanishes.
Yes. Without a strong, sustained error signal propagating backward through the network, the model just stops updating its complex cross-layer routing mechanisms.
So the knowledge gets successfully written into those easy-to-fit storage states at the loading dock, but the training signal literally dies before the model is forced to build an attention pathway to the mid-layer reasoning circuits.
Precisely. The knowledge becomes mathematically stranded. And they discovered a very distinct two-cluster pattern mapped out in Figure 5 that visualizes this perfectly.
What's the pattern?
When they looked at where the source knowledge was successfully stored, the effective representations clustered tightly around the early layers, roughly 0.1 of the way through the network's depth. And there was another cluster at the very late layers, around 0.8.
But the target layers where the self-patching intervention actually triggered the reasoning circuits, those were clustered right at the 0.5 mark, right?
Yes. The assembly line is strictly in the middle.
Wow.
And your factory analogy holds perfectly for those late layers. If you manually relocate a hidden state from the loading dock to the shipping bay to those 0.8 layers, it is utterly useless.
Because the reasoning stream has already finalized its logic by that point.
Exactly. The assembly line is shut down, and the model is just preparing to output tokens. Dropping raw materials at the shipping bay won't help you build a product.
So the bottleneck is strictly this misalignment between where the fact is stored and where mid-layer computation occurs.
Right. They formally call this the knowledge circuit misalignment hypothesis.
So what does this all mean? Like, practically speaking, it's one thing to diagnose a stranded representation. It's another thing entirely to fix it on the fly. If this is just a routing problem, can we intervene during inference?
We can, and with dramatic results.
Wait, we can manually move the materials to the assembly line to force the model to reason correctly without retraining it?
Yes. They implemented what they call Oracle self-patching. For a given inference instance, they search all possible layer pairs to find the optimal relocation path for the head entity representation.
And moving it to the best possible mid-layer.
Right. They tested this across the Quinn 2.5 architecture from 1.5 billion up to 7 billion parameters, and the Alame 3.1 and 2.2 families, up to 8 billion parameters. The manual relocation lifted the chaining task accuracy by 1.5x to 6x.
6x!
That's insane. And for the intersection tasks, it virtually eliminated the knowing using gap entirely.
I mean, I'm glad they ran rigorous ablations on this because that sounds almost too good to be true. Did they test standard prompting techniques against this, like chain of thought?
They did. You'd assume CoT would force the model to naturally route the information by expanding the context window. But while Co helped a little bit with chaining, it still lagged massively behind the self-patching intervention.
Makes sense. If the internal wiring is physically broken, generating more tokens doesn't necessarily fix the route.
Exactly. In fact, in some of the intersection tasks, CoT actually degraded the model's performance.
Interesting. And what about the token position? You mentioned they patched at the head entity token. Is that specific position required?
Oh, it's hyperlocalized. You must patch the hidden state at the head entity token. If you attempt to patch at the beginning of sequence token, or just pick random tokens in the prompt, the intervention does absolutely nothing.
Wow, so the factual representation is tightly bound to that specific entity in the residual stream.
Right, and that is exactly what must be relocated.
But practically speaking, the Oracle method requires a massive search, right? Searching every possible layer pair to find the optimal source and target for every single inference request. That's ON squared complexity over the layers.
It's completely computationally unfeasible for real-world deployment. You can't run a grid search inside your forward pass in production.
Yeah, that would destroy your latency. So what's the workaround?
That is the exact roadblock they anticipated, which led them to design the fixed heuristic. They analyzed that two-cluster pattern we talked about and realized they didn't need to search dynamically.
Oh, because the clusters are somewhat static per architecture.
Yes, they created a dirt-simple heuristic using just two predetermined layer pairs based on the specific model's architecture. One pathway moves hidden states from a static late layer to a static mid layer.
And the second pathway
moves them from a static early layer to a static mid layer. There is 0 per instance searching.
Okay, so did bypassing the search and just hard-coding the layer hops actually recover the reasoning performance?
It did. That fixed heuristic strategy recovered between 58% and 75% of the total Oracle headroom.
That is massive for a zero search heuristic.
Just by forcing the architecture to blindly hop the representations into the mid layers, they bypassed the majority of the fine-tuning failure.
If we connect this to the bigger picture, I mean, the takeaway isn't necessarily that everyone watching this video needs to go write custom inference scripts to hack their attention layers in production.
Right. It's a great band-aid, sure. But the real breakthrough is a fundamental shift in how we view the model's capability.
It proves the generalization failure during fine-tuning is a tractable alignment problem. The model isn't too small. It's not incapable of multi-hop logic with new facts.
Exactly. It possesses the reasoning machinery. It simply lacks the internal plumbing to connect the newly formed memory to that machinery.
Which really paves the way for, like, alignment-aware training, where we can design loss functions or training curricula that explicitly force the network to construct those routing pathways, rather than just treating the symptom at inference time.
It's a massive deal for the future of fine-tuning.
So, to summarize this for everyone building with these models, LLMs failing to reason with newly injected facts is a routing failure. The knowledge is in there, but the training gradient vanishes before the model can build a path to the assembly line.
And importantly, the researchers have open-sourced all their code and their specialized memorization to generalization data set. So if you're dealing with enterprise knowledge rafts and your RJ pipelines aren't cutting it, You can pull this down and experiment with the intervention on your own architectures.
It's a phenomenal resource for anyone trying to make fine-tuning reliable for mission-critical logic rather than just superficial style transfer or basic memorization. And I want to leave you with a final thought to mull over, building on that vanishing gradient issue we discussed. If injected knowledge gets stranded purely because the fine-tuning loss drops to near zero the moment simple memorization is achieved, how might we redesign our loss functions?
That's a zillion-dollar question.
Could you mathematically penalize stranded representations during the training phase? Imagine a custom loss function that refuses to converge unless it detects that the knowledge representation is actively accessible by the mid-layer reasoning circuits before the gradient is allowed to vanish.
That would radically alter the efficiency of fine-tuning.
Think about how powerful that would be. Let us know how you would approach building that penalty in the comments. We'll see you in the next deep dive into the paper.